Okay, so now we want to talk about limits. And remember that, so we have discussed this before in chapter number 3, that every real number has a decimal expression like this, that b naught, b1, b2, up to so on, represents the real number. That is the sum to infinity of a series. And that series is b naught plus b1 over 10, b plus b2 over 100, plus b3 over 100, 1000, and so on. Now, in this chapter, we am we we aim to make this statement precise, more precise. And to do so, we need to introduce one of the basic concepts or the fundamental concepts in mathematics, that is the limit of a sequence of real numbers. Now, first we need to say exactly what we mean by a sequence. So to do that, a sequence is just an infinite list of a1 of numbers, a1, a2, a3, an, and so on, of real numbers. In a definite order, in a definite order, the number an is the nth term of the sequence, and a1 is the first term. And we usually denote such a sequence by this symbol. Okay, so some simple examples of a sequence. Number one is 1 dot, sorry, 1 comma 1 comma 1 comma 1 is the sequence an where an is 1 for all n. Actually, sequence number 2 is going to be 1, 1/2, 1/3, 1/4, and so on. And this is the sequence with nth term is equals to 1 over n for all n. Number 3 example can be that if an is minus 1 power n, the sequence an is going to be minus 1, 1, minus 1, 1, and so on. Similarly, number 4 can be that we can define nth term to be 10 power minus 6 if n is prime, and 1 over n if n is not prime. Then the sequence an is going to be 1, 10 power minus 6, 10 power minus 6, 1 over 4, 10 power minus 6, 1 over 6, 10 power minus 6, 1 over 8, 1 over 9, 1 over 10, 10 power minus 6, and so on like this. So remember, the values for n is going to be natural numbers. So we have, for 1, we have 1. For 2, we have 10 power minus 6 because n is prime. So for every n is prime, you will write 10 power minus 6. And for every other n, you will write 1 over n. Okay? That's how we can define the sequences. Multiple examples. We now want to define the limit of a sequence. Now, intuitively, as discussed in chapter number 3, this should be a real number a, such that we can make all the ans as close as we like to a, provided we go far enough along the sequence. Now, how do we make this mathematically precise? To say that we can make the ans as close as we like to a means the following. So for that, what we need to do is to pick a real number. So what we mean by, so you can say, to say that we can make the ends is close as we like to some real number, some a in real number a means the following. That means if we pick any positive real number epsilon, however small, all the ans beyond a certain point lie between a minus epsilon and a plus epsilon. So this is, we mean when we want to say that the sequence is as close as we like to some real number a, is to, if we pick, now is means that we pick a positive real number epsilon, however small, we don't care, all the ans beyond a certain point lie between the values a minus epsilon and a plus epsilon. Now, to give this a formal definition, we will write a definition. Definition is, we say that a sequence has a limit a if the following is true. Given any real number, and that real number is epsilon, which is greater than 0, there is an integer n which depends on epsilon, such that all the terms an for n greater than or equal to n lie between a minus epsilon and a plus epsilon. Now, that's the definition, which says that a sequence an will have a limit a. Now, this definition is often written a little more hard as follows. So we say that for any epsilon greater than 0, there exists some integer n such that absolute value of an minus a is less than epsilon for all n greater than or equal to n. Okay. Now, if the sequence n has a limit a, we write that a, we write that a is going to be lim of an, or an goes to a, and say that an tends to a to the limit a even. Okay. Now let's give an example to understand this more precisely. So we are saying that we have an example 23.2, and we will examine the sequences in example 23.1. So number 1. So the first sequence was only 1, 1, 1, 1, and it is hard to imagine the limit of this sequence, but anything but 1. So the sequence is 1, 1, 1. So the limit of this sequence is nothing but 1. Now to see this, we apply the definition. So we will say let epsilon is greater than 0 be any positive number, then taking n is 1, we have mod of an minus 1 is less than 0 or even equal to 0, which is less than epsilon for all n greater than or equal to n. So according to the definition, limit an going to be is equals to 1 as expected. Now, number 2, the sequence is one, 1, 1/2, 1/3, 1/4, 1/5, and the n term is 1 over n. Okay. Now we show that the limit of the sequence is 0. How? Let epsilon is greater than 0. Choose an integer n greater than 1 over epsilon. Then for n greater than or equal to n, an minus 0 is nothing but 1 over n less than or equal to 1 over capital N, which is less than or equal to epsilon. Hence, sequence goes to 0. Now, the important thing is to note that the order of events in the definition of a limit is very important. It's very, very important because if you change the order, then you might not get the proper limit for the sequence. So that's why we cannot mess with the order. Like, as you can see, first we are given any number, any real number epsilon, which is greater than 0. And then we find an n that works as in the second example above. Now, n usually depends on epsilon. Reversing the order of events and writing that there exists n such that for any epsilon greater than 0 will have a quite different meaning. And that will not give us a proper limit. So let's try another example. So the third one. Now let's examine the third example. In the third example, actually the third sequence, an is going to be minus 1 power n, and it does not have a limit. Here is a proof of this by contradiction. So to see that, suppose the sequence does have a limit. Then we call it A. To obtain a contradiction, we need to find a specific value of epsilon greater than 0, for which there is no n such that this absolute value of an minus a is less than epsilon for all small n greater than or equal to n, capital N. Now let epsilon is 1 over 4. Then whatever a is, either 1 does not lie between this or minus 1 does not. So if, let's say, epsilon is 1 over 4, then whatever a is, either 1 does not lie between a minus epsilon and a plus epsilon, or minus 1 does not. So whatever n we try, there will be a value of small n greater than or equal to the capital N, such that the absolute value of an minus a is going to be greater than epsilon. Hence, there is no n. Hence, there is no n which works in the definition of a limit. Of a limit for epsilon is 1 over 4. Now this contradiction shows that an does not have a limit. Sequence does not have a limit. Perfect. Now we will talk about the number 4. Now the sequence which number 4 was that if n is prime, we have 10 power minus 6, and if n is not prime, I think an is equals to 10 power minus 6. We have an is 1 over n. Now this sequence an also does not have a limit. Now we prove this in a similar way. So by contradiction, by contradiction, suppose that an goes to a. Now, if a is not equals to 10 power 6, let epsilon is the absolute value of 10 power 6, 10 power minus 6 minus a, which is greater than 0. Now, as an goes to a, there exists some natural number n such that the absolute value of an minus a is less than epsilon for all small n greater than or equal to n. However, there is a prime. There is a prime p which is greater than n by Euclid's theorem. By Euclid's theorem 12.1, and we have AP is equals to 10 power minus 6. Then absolute value of AP minus A is nothing but 10 power minus 6 minus A is not less than epsilon. Not less than epsilon, which is a contradiction. Which is a contradiction. Okay. Now, hence, A must be 10 power minus 6. Now, take epsilon is equals to 10 power minus 6 by 2. Is an goes to A, which is 10 power minus 6. There exists n such that an minus a, which is 10 power minus 6, absolute value of that is less than epsilon for all n in n is greater than or equal to n, but for any positive value of n greater than 2 into 10 power minus 6, we have an is equals to 1 over n, which is less than 10 power minus 6 over 2, comma, hence an minus 10 power minus 6, absolute value of that is greater than 10 power minus 6 over 2, which is epsilon. This is also a contradiction. This is a contradiction. So hence, in general, the sequence does not have a limit. Okay, so that's number 4. Okay, so by this example 23.2, we analyze that some sequences have a limit, some sequences does not have a limit. Now we call a sequence that has a limit a convergent sequence. So the sequence which has a limit has a limit is called a convergent sequence. Otherwise, it is divergent. Otherwise, it is divergent. Okay, so in example 23.1, 1 and 2 are convergent sequences. Right. Perfect. So let's define some other example, which is little trickier than the previous one. So this is example 23.3. Let A and B a sequence, be the sequence with the nth term is equals to 3n square plus 2n plus 1 divided by n square minus n minus 3. The question is AN convergent? And if so, what is its limit? Is AN convergent? Is the sequence convergent? If so, what is its limit? Let's find out. To find the limit, if you write AN is 3 plus 5n plus 10 over n square minus n minus 3, seems plausible that sequence should be convergent and have a limit 3. It seems plausible that AN should be convergent and has a limit 3. Let's try to prove this. So let epsilon is greater than 0. We want to choose n such that choose n such that n, small n, is greater than or equal to n. To do that, we have an minus 3 absolute value is going to be 5n plus 10 over n square minus n minus 3 less than epsilon. Now it looks awkward to calculate what n should be, but we can simply simplify things by observing that provided n is greater than 10, we have 5n plus 10 over n square minus n minus 3 less than 6n over 1 over 2 n square, which is 12 over n. Now, by this, we can choose n to be greater than both 10 and 12 over epsilon. So hence, if we choose n to be greater than both 10 and 12 over epsilon, then for any small n greater than or equal to n, we will have an minus 3 absolute value is equals to absolute value of 5n plus 10 over n square minus n minus 3. Absolute value will be less than 12 over n, which is less than epsilon. This proves the limit of the sequence is 3. This proves the limit of the sequence is 3.